some basic concepts of chemistry. That is the first chapter of class 11th. So to begin with, the importance of chemistry. As you see here, chemistry is applied in many fields like community, health, environment, medicine, industry, sciences, teaching, research, and of course you. Your body contains cells which contain atoms and molecules of various substances. If the biochemistry of your body is disturbed, you have to take medicines, and these medicines are also chemicals. So here you have to learn a few things, that is life-saving drugs. Cisplatin and Taxol are important drugs for cancer therapy. AZT, that is azithromycin, is important in AIDS treatment. Then about SI units. SI units are for 7 basic quantities. 3 quantities we have studied in previous classes, that is length, mass, time. The MKS system, the CGS system you have studied. But here you have to learn 7 basic units, SI units of 7 basic quantities. Length has unit meter as in MKS system. Mass has kilogram. Time has second. Now the other quantities which you have to learn this year are electric current. It has a unit ampere. Thermodynamic temperature. It has SI unit Kelvin. Amount of substance has unit mole. Luminous intensity has unit candela. So these you have to learn. The symbols of quantity as well as symbols for SI units are given in the table. You must learn these. Then about mass and weight, the difference you have to learn. The mass can be defined as the amount of matter in the body. Weight is due to the pull of gravity on the body by the center of earth. Mass has only magnitude, that is, it is a scalar quantity, whereas weight is a vector quantity. It has both magnitude and direction. Direction is towards the center of the earth. Mass is measured in kilogram, weight is measured in Newton. Mass remains constant regardless of place or location, whereas weight changes from place to place. It depends on the value of small g, that is acceleration due to gravity. One more difference is there. Mass is measured by a beam balance, whereas weight is measured by spring balance. Now, volume has SI unit of meter cube. You must know the relationship between the SI unit and liter. Liter is used for measuring liquids. It is the unit of volume for liquids. So, you can remember this relation by the simplest relation, that is 1 ml is equal to 1 centimeter cube. So 1000 ml is equal to 1000 centimeter cube. And the common mistake children do here, they write 1 liter is equal to 1 meter cube, which is not so. You can see here 1000 centimeter cube is equal to 1 decimeter cube. So this you have to remember. Then about density. Density is mass per unit volume. Its unit is kg per meter cube, that is the SI unit. You can convert it to gram per centimeter cube by putting the values of kg and meter in this formula. You can write 1000 kg, you can write 1000 grams for kg, and for meter, in place of meter you can write 100 centimeter. That is how you can convert to gram per centimeter cube. Then temperature has different units. In daily life we use degree centigrade and degree Fahrenheit, whereas the SI unit is Kelvin. Now you can see here the 3 thermometers are shown here, Kelvin, Celsius and Fahrenheit. We can see here that Kelvin starts from 273 and ends at 373 Kelvin. Celsius scale starts from Celsius or centigrade is same. It starts from 0 degree to 100 degree. Then Fahrenheit starts from 32 degree to 212 degree. Now for finding the relationship between these 3, we can write here, as you see here, degree centigrade, it starts from 0 and it has 100 divisions. Degree Fahrenheit, it starts from 32, it has 180 divisions. Kelvin starts from 273, it has 100 divisions. So if you find the relationship between these, the first relationship, you can equate the first and last quantity. We get degree centigrade is equal to K minus 273. So if you know the temperature in Kelvin, you can convert it to degrees centigrade. Like for 273 Kelvin, if you put 273 in place of Kelvin, you will get 0 degree centigrade, as you can see here also in this pic. 273 is 0 degree centigrade and it is equal to 32 degree Fahrenheit. So for other temperature also, you can put different values for Kelvin and get the value in degree centigrade. Similar is the case for Kelvin. You can find the temperature in Kelvin by putting the value of Celsius in place of degree centigrade. Like you can see in this room temperature, we have 25 degrees centigrade. So if we put 25 degrees centigrade in this centigrade position, you will get 298. That is the room temperature in Kelvin, as you see here. So similarly, you can find the relationships by equating the first two quantities, this and this, and you get the relationship between degree centigrade and degree Fahrenheit. So these two relations are to be remembered for converting the temperatures from degree Fahrenheit to degree centigrade and vice versa. Degree C is equal to 5 by 9, degree F minus 32. Remember to put the brackets here. And in case you have to find degree Fahrenheit, it is 9 by 5 degree C plus 32 and no bracket here. So these are the things to be remembered. Significant figures. There are certain rules to count the number of significant figures which are different for physics and chemistry. You can see here the terminology. The zeros marked with blue are termed as leading zeros. That are the zeros before first non-zero digit. Then non-zero digits, in between zeros, and in the last we have trailing zeros. These are all significant, whereas leading zeros are insignificant. Let's see the rules. Counting significant figures. First rule says all non-zero digits are significant. So we have 1.5 example here. It has two significant figures, 1 and 5. Then interior zeros between two digits, they are significant. 1.05 will have three significant figures, all the three. Then trailing zeros after a decimal point are significant. Example is 1.050. So all the four are significant, all the four digits. So we have four significant figures here. Then leading zeros, that is the zeros before first non-zero digit, they are insignificant. They are not counted. So this example 0.001050 will have four significant figures. Then zeros that do nothing but set the decimal point, means at the last they are not significant. So 150, the last zero just shows the position of decimal point, which is not shown here. So it has only two significant figures. This is something you have to remember, which is different from the normal practice. So 150, 15, 1500 all will have two significant figures. Another example is shown here. The last zeros are not significant, so this number has only three significant figures. Again, an example is shown here. The significant or non-significant zeros and the digits which are significant are shown here. You can see the marked ones with blue are insignificant, where those marked with pink are significant. Then some more examples. 23.50, all the four are significant, four significant figures. Then 402, all the three are significant. 5280, the last zero is insignificant, so it has three significant figures. 0.080, the leading zeros, the first two zeros are insignificant, so it has two significant figures. Then exact numbers have infinite number of significant figures. As you see in the example, we can write 2 is equal to 2.0000 or 20 is equal to 20.000. So if some counting things are given like 2 balls or 20 eggs, they have infinite number of significant figures, as they can be represented by writing the decimal zeros after the decimal place. So we have infinite number of significant figures in 2 balls and in 20 eggs, or in 30 pencils, or 300 mangoes, anything like that. Significant figures in calculations. For multiplication and division, we have to report the answer with least number of significant figures. That is, you can see in the example here of these two numbers, the least number of significant figures is 2, so answer is to be reported up to 2 significant figures. Same rule holds for division. Answer should have minimum number of significant figures of the numbers involved. For addition and subtraction, we have to see the number of significant figures after decimal place. After decimal place, the number of significant figures should be least as present in the numbers involved. So in this example, we have least number is 0 decimal place. Okay, so the answer to be reported to 0 decimal place. So 146.1 is to be rounded for 0 decimal place, that is 146. Same rule holds for subtraction. Means least number of significant figures are to be there in this, both the cases. Here are some practice problems. Answer are shown over here. One thing you have to see here. In case of scientific notation, the significant figures are seen only in the whole number part. The 10 to the power part is to be left. So 7.09 into 10 to the power minus 5 will have 3 significant figures. For this one, you can see the first number has 4 significant figures, whereas the other number has 3 significant figures. So answer to be reported to 3 significant figures here. Similar is the case for other. So next we have atomic mass. Atomic mass of an element is the number of times an atom of that element is heavier than an atom of carbon, taken as 12. So 1 atomic mass unit AMU is equal to 1/12 of the mass of an atom of carbon-12 isotope. Nowadays AMU has been replaced by U, which is unified mass. The examples are shown here. The atomic mass of carbon is 12 units, atomic mass of oxygen is 16 units. Similar is the case with other elements. Nitrogen has 14 units atomic mass, hydrogen has 1 unit atomic mass, and so on. Then this is something to remember, average atomic mass. This is taken when there are several isotopes of a particular element. When they exist in nature, we have to take the average mass of these isotopes by taking into account their natural abundance. An example is shown over here. Chlorine has 2 isotopes, Cl35 and Cl37, and they are present in 3:1 ratio in nature. So we can calculate the average atomic mass like this: 35 into 3 plus 37 into 1 divided by 3 plus 1. So it comes out to be 35.5 units. That is the atomic mass of chlorine we use. Then molecular mass, it is calculated by the atomic masses of the elements. So examples you can see. This is also a relative mass in relation to carbon-12 atom. So examples you can see here. Molecular mass of hydrogen water can be calculated as 2 into 1, as 2 atoms of hydrogen are there and mass of 1 atom is 1. So 2 into 1 plus 16, that is the mass of 1 atom of oxygen. So it comes to be 18 units. Now in case of NaCl or any other ionic compound, we calculate the formula mass. Why formula? Because NaCl does not exist as discrete molecules. So ionic compounds, they have crystal lattice. So we calculate the unit mass for formula. So NaCl mass can be calculated in the same manner as molecular mass. So it has the mass 23 plus 35.5, that is 58.5 units. Next is molar mass. Molar mass is mass of 1 mole particles of a substance given in grams. It can be mass of 1 mole atoms, it can be mass of 1 mole molecules, it can be mass of 1 mole ions. In case of atoms, we can write gram atomic mass for molar mass. and it is the mass of 1 mole atoms of a particular substance. It is find out by putting gram in place of unit in atomic mass. So carbon has atomic mass of 12 units. We can say that 12 grams of carbon is the mass of 1 mole atoms of carbon. Similarly, 1 gram of hydrogen is the molar mass of hydrogen. That is, 1 gram of hydrogen will contain 1 mole atoms of hydrogen. Similar is the case for gram molecular mass, that is molar mass of some molecule. So for hydrogen, at molecular mass is 2 gram. So gram molecular mass or molar mass will be 2 grams. For oxygen molecule O2, 32 units is molecular mass and 32 grams is the molar mass of oxygen, that is mass of 1 mole molecules of oxygen. Now the mole concept, very important. This you have to remember. 1 mole is the value, that is the Avogadro number. It is equal to 6.022 or 6.023 into 10 raised to the power 23 particles. This is equal to gram atomic mass or gram molecular mass, that is the molar mass, and this is equal to 22.4 liters of gas at STP. STP is what? STP is standard temperature and pressure. Standard temperature is 273 Kelvin and standard pressure is 1 bar, that is equal to around 10 to the power 5 pascals, also equal to 1 atmosphere. And in case of barometer, it is the 76 centimeter reading in barometer or 760 millimeter of the column height of mercury. So this concept you have to remember. You will be having numericals based on these. Let's see some examples of mole concept numericals. Before that, see this mole map, how to convert. See, moles can be converted to grams by multiplying the number of moles with molar mass, and vice versa. When you have to convert to grams to moles, you have to divide the grams, given grams, by molar mass to get the number of moles. That is, number of moles is equal to weight in grams upon molar mass. For converting volume and moles, conversion of moles to volume, we have to multiply it by 22.4 liters because 1 mole is equal to 22.4 liters and the given moles will be the product of number of moles and 22.4 liters, and vice versa also. Then moles to number of atoms, 1 mole is 6.022 into 10 to the power 23 atoms. So the given number of moles will be equal to number of moles multiplied by this Avogadro number. So this you have to remember for doing the numericals. Let's see few examples now. Mole to number of particles. How many moles are there in 0.5 mole of hydrogen gas? Now we know that 1 mole is equal to these many particles. So after 1, when you have to find any other, you have to multiply. So 0.5 mole will be 0.5 into this value. So we get 3.011 into 10 to the power 23 molecules. Next we have mole to mass. Let's see the example. What is the mass of 2 moles of oxygen gas? Now we know that 1 mole of oxygen gas will be equal to its molar mass, that is 32 grams. So 2 moles will be 64 grams. Next, mass to volume, mole to volume. How much volume is occupied by 2 moles of nitrogen gas at STP? Here you can see 1 mole at STP of any gas is equal to 22.4 liters. So 2 moles will be 2 into 22.4 liters, that is 44.8 liters. Another conversion. Now here we have to start with a value other than 1. So 2 steps are there. Unitary method is followed. First you have to find the value for 1 and next for the given asked thing. How many moles are there in 3 into 10 to the power 22 atoms of carbon? Now from the known equation we know that 6.022 into 10 to the power 23 atoms of carbon, this is equal to 1 mole. See, you have to put that thing on the right hand side, which you have to find in the known equation. You have to find the number of moles. So in given equation, in known equation, you have to put moles on the right hand side. Now you have to find this value for one atom. So this comes in denominator. And one thing to remember, you need not calculate here. Calculation is to be done in the last step. Now for finding the number of moles in 3 into 10 to the power 22 atoms, we can multiply this value with the value for one atom and get the answer. That is 0.5 into 10 to the power minus 1 mole, or simply you can write 0.05 mole. This is how you have to calculate. Let's see one more example. Number of particles to mass. What is the mass of 2 atoms of carbon? Now this is something important and asked in exams also. You have exercise question also. What is the mass of 1 atom of carbon in grams? So here you have to start with the Avogadro number of particles is equal to molar mass of that substance. With the change of substance, the mass changes. For carbon, it is 12 grams. These many particles equal to 12 grams. So for one atom, this mole value, this comes in denominator. So for 2 atoms, you have to multiply and we get 4 into 10 raised to the power minus 23 grams. This 6.022 can be rounded off to 6 for calculation. Another example, number of particles to volume. What volume is occupied by 6 into 10 to the power 22 molecules of hydrogen gas at STP? So in given known equation, we have 1 mole of particles, that is 6.022 into 10 to the power 23 molecules of hydrogen at STP occupy 22.4 liters. So 1 molecule will occupy 22.4 divided by these liters, and 6 into 10 to the power 22 molecules will occupy, this value is to be multiplied and you get the answer as 2.24 liters. So that's all for this video. You can have many more examples in your book and in refresher books. Try to solve these. Thank you.